Good afternoon. Welcome back to Mass 814, Algebraic Theory of Semigroups. So last time we looked at two definitions or two theorems. Actually, we look at the concept of groups, semigroups that are groups. And then we also look at zero semigroup or zero group. Zero group are semigroup for which semigroup is zero, for which the removal of zero leave out a group, like the semigroup of real numbers under multiplication. It's a zero group because zero is there, but when you remove the zero, you no longer get you get a group, but originally it was not a group because of the existence of zero element. And then we saw some necessary and sufficient condition for a semigroup to be a group, and also for a semigroup with zero to be a zero group. So we are still talking about basic concepts of semigroup. So actually we have not started the theory properly. We are looking at some preliminary concepts. I think what we are going to talk about now is the concept of subsemigroup. So I start with the definition of what is called subsemigroup. So a non-empty subset, T of a semigroup S is called a subsemigroup of S if for all A, B in T, A times B is in T. That is all. Well, you can see that it's not difficult to check that a subset is a subsemigroup because you only need to check closure property. Once it is closed, this is what this means. In fact, in our notation, if T square is a subset of T, because T square will consist of all product AB, such that A and B are coming from T. Is this okay now? So once you see that T is closed under the binary operation, then it is a subsemigroup. Like which one? Look into the semigroup of integers with multiplication. If you take the even integers with multiplication, is it a subsemigroup? Multiply any two even integer, it still get even integers. So likewise, if you take the odd numbers, odd integers with multiplication, product of two odds is also an odd. Is that true? Set of odd integers. Yeah. But how about if I take integers with addition? This is a group. It's already a group. Okay. Then you know when you remove the zero, you don't get a group. Okay, let me give you more examples. So if S has an identity and zero, identity element 1 and zero element 0, then the sets, the subsets are both subsemigroups of S. Now, if you take the identity element of the semigroup as a singleton, identity, whenever you multiply, you still get the identity back. Likewise, if you take the zero element and multiply, you get the zero. You get the zero element back. So this is forming a subsemigroup. These singletons are forming subsemigroup. So you can have so many. You remember in group theory, the only singleton subgroup is a trivial one, the one consisting only of the identity. But in semigroup, you can have two of them, at least we can see. If the identity is there, we have a semigroup. If zero is there, we have a semigroup. Like if you take this identity from here, it has identity. So it has a singleton subgroup, subsemigroup. And it also has zero. If you take the zero alone, you also get a subsemigroup. Do you get it? So these are trivial examples of subsemigroups. When you regard the singleton zero as a subsemigroup, now the element zero is no longer the zero of that subsemigroup. So if you take T to be the singleton in a semigroup with zero, for example, if one asks you what is the zero element of this semigroup of integers, it is the number zero. Are you following? Now if I take that number zero and see T as my subsemigroup here, is this a semigroup with zero or not? That's the point I'm trying to make. Yeah, is T now a semigroup with zero? No. I pick the zero element and see it as a singleton to form a subsemigroup. Now, this zero was the zero element of the bigger semigroup, but now inside the smaller semigroup, is it the singleton? Is it a zero element? No. It's no longer a zero element here, but an identity element. So it is now regarded as identity element, not zero element. I hope it's okay. Because a semigroup with zero must have at least two elements. Since there is only one element here, namely zero, we regard it as identity. So something that wasn't identity from the original semigroup is now identity. I hope it's okay. So you have to take note of this kind of situations that may arise. Okay?
What if you to be the identity?
Yeah, this is still identity. It's still identity here. Yeah, this is still identity of that subsemigroup, and this is still also, this will also be identity of the subsemigroup. Okay. An element. So let me give you a definition now here. An element E of S, a semigroup S, is called an idempotent if E square equal to E. This kind of elements are existing in many examples of semigroups. So in a semigroup, apart from identity element, you remember identity always, the square of identity, you always get identity. So but apart from identity element in a semigroup, you can get so many elements whose square equal to themselves. Such type of element are called idempotent. And identity is one example of idempotent. Zero element is also an example of idempotent. The identity and zero are all idempotent in the semigroup. And so it is also true that if you pick an idempotent, the singleton containing idempotent is also a subsemigroup. So in a semigroup where there are idempotent, each idempotent will form a singleton subsemigroup. So you can have so many singletons of semigroup in a semigroup, unlike in the situation of group. In fact, these idempotent are the ones that are giving rise to singletons of semigroups. What happened in group theory was that The only idempotent is the identity. And so that's why you have only one singleton subgroup, the trivial one. I hope it's okay. But in semigroup, you can have so many, okay, of them. But like here, you can see this is an idempotent. I have two idempotent here. So I have the singleton and I have the singleton. So there will be as many singletons of semigroup as the number of idempotents in the semigroup. Is this okay now? Yeah. So the subsemigroup that is sitting properly inside, not any one of these ones, will be called proper subsemigroup. Okay? So maybe I will just suspend this issue here and define the notion of an ideal. So a subset, so non-empty subset also, A of a semigroup S. So S is called a left ideal if SA is a subset of A. What does this mean? If I pick any element of the semigroup and multiply with an element of A, I get inside A. This is a left ideal. Are you following? And a right ideal, yeah, a right ideal if AS is a subset of A. Number three, a two-sided ideal, so maybe it should be put in. A two-sided ideal, so, but this prefix doesn't have to always come. Two-sided, you can just call it an ideal. So you don't have to emphasize two-sided, or you can just say an ideal. If it is both left and right ideal. So an ideal which is both left and right ideal is a two-sided ideal. Like if the semigroup is already commutative, every left ideal will also be right ideal. So every ideal of whichever direction is also an ideal. Are you following? So in a commutative semigroup, there is no distinction between left, right. So everything is an ideal automatically. Okay? We have example. Like if you are in the group of semigroup of natural numbers with addition, you take the set of even natural numbers. Even natural numbers is an ideal. Okay?
Natural numbers with zero.
No, whatever. No, whether you take with zero or anything. So the even natural numbers with multiplication, this is an ideal. Yeah, because if I take an even number and multiply with any other number, the result is an even number. I hope it's okay. But look at this set of odd natural numbers. It's not an ideal. If you take 3 and multiply with 2, you don't get an odd number. Are you following? So this is not an ideal. Okay? In fact, we can prove that it's very easy to see. It is clear from the definition that every ideal, in fact, every left, right, or two-sided ideal is a subsemigroup. An ideal is always a subsemigroup. Why?
It's closed and associated.
Why is it closed?
Because when you pick any,
You say SA is in A, but then always A square is in SA. So if SA is in A, then definitely A square will always be in A. This is true with right ideal. So every ideal is always a subsemigroup, but not conversely. The converse is not true. The fact that A square is in A doesn't mean SA is in A. Like the odd numbers. If I multiply any two odd numbers, I get an odd number. So it's close with respect to multiplication inside in the subsemigroup. So this is a subsemigroup but not ideal. If you take an even number with an odd number, you get even if you do the multiplication. Are you following? But here, if you multiply any two even, it's still an even. And if you take odd and multiply with the even, you still get even. I hope it's okay. So this is an ideal. So every ideal is a subsemigroup, but not conversely. There are subsemigroups that are not ideal. So this ideal are subsemigroup with some additional property or additional power. The power of absorbing element from the larger semigroup. Okay? You have the big semigroup, you have the small subsets, and then if you take any element from here and any element from the big semigroup and multiply, the resulting product will fall inside the smaller portion for the right ideal. For the left ideal, if I do the multiplication like this, it's still inside. If it is already an ideal, then any side from both way you multiply, you get inside. So these are like absorbing subset that absorbs all others. But in fact, even if you take from here, A, B will still be inside. So it is always a subsemigroup. So these ideal are nice subsemigroups, stronger ones. They will be like the analog of normal subgroups in group theory. Normal subgroup are the more interesting subgroups than the general subgroups because they are the ones you use to subdivide the group into classes. Okay? So like ideas also they can be used to subdivide the group into classes. We'll see that construction called Rees quotient. We'll see that. So if a semigroup S has 0 element, this, well, no, 0 element, 0, then the singleton is always an ideal. An ideal of S meaning it is both left and right ideal. Because anything you multiply with 0, you get 0. So the entire product is always inside there. Are you following? 0 is a very powerful element of the system. Now, an ideal I of S such that I sits properly between the semigroup and S, but I haven't mentioned S is also an ideal of itself. S is an ideal of itself. Like it is a subsemigroup of itself. Every subset is a subset of itself. So every semigroup is a subsemigroup of itself. This thing is also there for group. So S is an extreme example, and 0 is also at the other extreme. Any other ideal sitting in between is called proper. Okay? Proper ideal. So I can still. Otherwise, it is improper. It means S and the 0. These are the improper ideal. Are you following? Proper ideal. Like proper normal subgroup. So you can guess now, what should be called simple group if it has no proper normal subgroup? So what should be simple semigroup?
If it has no proper normal ideal.
Normal, no proper ideal. Not normal ideal. If it has no proper ideal. So a semigroup with no proper ideals is called simple semigroup. But then, 0 is proper actually in the sense of subsets. If it is a semigroup with 0 and the only ideals, because if it is a semigroup with 0, this 0 will always be there as an ideal, and S is always there as an ideal. So, but if there is no any other ideal apart from these two, then you call it a 0 simple semigroup. Just to pronounce a semigroup with 0 that has no proper ideal except the 0. I hope it's okay. All right. We are coming to that discussion. In fact, this will be the topic of chapter 3 of this material we are following, fundamentals of semigroups. Okay? So, I will prove a lemma to the effect that if you take the intersection of two ideals, you still get an ideal. I think I'm not going to prove it, but I will just leave it to you as an exercise. It's not difficult. So lemma 1.5. 1.5? Okay. 1.4, thank you. So in a semigroup, the intersection of any two ideals is again an ideal. It's also an ideal. In fact, I think I should put it in this way: of any two left, right, or two-sided ideal ideals is also a left, right, or two-sided ideal. If you get two left ideal and intersect, the intersection is also an ideal. If you take two right ideal and intersect the two, it's also a right ideal. And if you take two-sided ideal, the intersection is also an ideal.
Any
left and right?
is intersection ideal?
No, not necessarily. Okay, you can try it. Okay. You take a left ideal and a right ideal and take the intersection. All right. Whether the intersection is an ideal or not. Okay? Can they even intersect? That's the first question. Well, if they intersect, whether it is left ideal, try it. Yeah, I haven't thought of it before. So, now, given, so I said I'm not going to prove this thing because it's straightforward. So, given um, a set of elements or an element, A in the semigroup S, there is always ideal of S, some ideal, or left ideal, left, right, or two-sided ideal of S containing A. This is always true. If all possibilities fail, take S. The entire semigroup is always a left ideal. It's always a right ideal. It's always a two-sided ideal. And the element is coming from it. Everything is from it. So every element of the semigroup always belongs to at least one ideal, namely the entire semigroup. One left, right, or two-sided ideal. Is that okay? So which means I can speak of the collection of all left ideal, or all right ideal, or all two-sided ideal of S containing A. And among members of that collection, S will be there. The entire semigroup will be there. Okay? And so the collection of all left ideals of S left or right or two-sided ideals of S containing A is not empty. That collection is not an empty collection. Okay? It cannot be empty. Why? Because we know at least there is always one ideal that will be present there, namely S, the entire semigroup. Is this okay? But then if you intersect two ideals, you get an ideal. The two left ideals or two right ideals or two-sided ideals, you still get an ideal. So which means this collection, if I intersect all its members, I still get a new ideal. And that new ideal will still contain what? A. Will still contain A. Because each one of them contains A. So, now the intersection of all the ideals, all the left, right, and two-sided ideals, or two-sided ideals. You know why I'm doing this? Because the discussion is the same as the left, right, and two-sided. It's just a, so that is why I'm just combining everything together. So if you take the intersection of all the left or the right ideal, all the two-sided ideals in this collection, is again a left, right, or two-sided ideal of S containing A. Ah, but then that means it is a member of that collection, because that collection involves all the ideals of S contained in A. I hope it's okay. So which means that intersection of all the members in there is also inside there, present. It has one extra property. What is that property? Apart from it being an left or right or two-sided ideal contained in A, it has one more extra property that other ideals in this collection are not having. What is that property? It is the smallest of all of them because it's the intersection of all of them. If you take two sets and intersect, the intersection will be smaller than each one of them. I hope okay. So it is also again an ideal contained in A and it's the smallest. And it is the smallest of all of them. And it is what? The smallest of all of the ideals left, right, or two-sided ideals in the collection. It is there present in that collection, but it is the smallest of all of them. We shall call it, so it's a characteristic property of that ideal. It's unique. You cannot have two smallest. It's unique. It's the only one there. We call it what? The principal ideal of S generated by S. Generated by A, the element A. So we call it the principal ideal. Oh, well, we are talking about left or right. If you are talking about right, it is the principal right ideal. If left, it is the principal left ideal. If two-sided ideal, so it's the principal two-sided ideal, of S generated by what? By the element A. The principal ideal generated by A. It is the intersection of all ideals of S containing A. Is that okay? Did you understand this concept? The what?
What of the union?
The union.
Is it also possible for the union? That is a only
Union of two ideals is not necessarily an ideal. Just like union of subsemigroups is not necessarily a subsemigroup. Like union of groups is not necessarily a group. Are you following? Yeah. Union of two groups, two subgroups, is not necessarily a subgroups. Union of two groups is also not necessarily a group. You have to, it's not necessarily a group because how do you define? Well, with respect to which multiplication? If you take two groups, a group G and group H, and take the union, the binary operation here and here may not be the same. So if you pick an element of G and an element of H, how do you combine them? They may be entirely different elements because this group may be of numbers, this group may be of matrices. How do you add a number to matrix? You may not know how to do that. Maybe. Union, the notion of subgroups is not closed under union, right? It is closed with intersection. If you take intersection, you still get a subgroup. Okay, so who can give me example of an ideal generated by some elements? like in the group of integers with multiplication, or these natural numbers with multiplication. Can you give me an ideal generated by 5, for example?
We have 5,
Yes. 5,
10,
10,
15.
15. What are you doing? You are picking multiples of 5?
Yeah.
How do you know to take multiple of 5?
We take by using
Because I said ideals in n with multiplication. You give me the ideal generated by 5, and you said I should take 5, 15, or 10, 15, and so on, all multiples of 5 you are picking. Yes, I say, how do you know to choose multiple of 5 to be the ideal generated by 5? Are you telling me that this is the smallest ideal of n containing 5? Is the smallest? Okay. No anyone can be smaller than this one.
it is containing
No any ideal can be smaller than this.
containing that.
Yeah.
Smaller.
Okay. So actually, if you are to use the definition, it's not practically possible to say you have to get hold of all the ideals containing A and take the intersection of all these ideals containing A, okay? And then before you can say this is the ideal generated by A. But what you are doing here is picking the multiples. Yeah, that is okay. That is always what needs to be done. So you take the multiples like this. You take n and multiply with A from where? Yeah, from left or right, because this is commutative situation. So this is generally true. In fact, we can generalize it as a theorem 1.5. We say that, so let S be a semigroup, well, semigroup, and A an element of S. And the principal left ideal, the principal uh, so left, right, or two-sided ideals of, let me just leave out the bracket, left, right, and the two-sided ideals of S generated by A are given by S1A. So this is the principal left ideal generated by A. S1 and what? S1A, S1 respectively. So this will be the principal two-sided ideal generated by A. The principal right ideal generated by A and the principal left ideal generated by A. Here, S1A, it means what? SA union A. You are introducing A there. I hope it's okay. It means like left coset, multiplying all element of S1. You know, this is with identity adjoint if necessary. And the AS1, it means AS union A. That is, you want A to be there always. And The other one is what? S1, A, S1. This is the same thing as, so it will be SAS union SA union AS union what? A. Yeah. So this is much bigger because it contains these two inside it. I hope it's okay. From the very definition of this multiplication, you can see that this set is bigger. In fact, it always contain the left and the right in it. All right. So let's prove this. Let us prove it. So proof. In fact, I'm just going to prove only one, the left, and then leave the remaining as exercise because they are proved similarly. So the first one, so we say suppose, so let A be the principal left ideal generated by what? By the element A. Then I want to show that this A is equal to S1A. Okay? So to do that, by the very definition of the principal ideal generated by A, it means this is the smallest left ideal containing A. So if I can show that S1A is an ideal and it contains A, then it must contain this capital A over there. Well, to see that it contains A is not difficult because by the very definition of it, this is it. So by the definition of S1A, it is immediate that you can see the definition A is an element here. Now, but this is this thing an ideal, a left ideal. Okay? So to see that S1A is a left ideal of S and now containing A, we take an element X from here, S, and take what? An element B, Y, well, or I call it B, I don't know. So what do? Maybe we take some element here, Y, to be in S1A. Then Y must be B, A, for some B in where? In S1. Then Y must be BA for some B in S1. B can be identity, the adjoint identity. In which case Y will be equal to A. And we have no problem. So, so what is X times Y? No, XY. Because we are trying to establish left identity. And so, XY is equal to XBA, which is equal to what? XBA. This XB must be what? An element of S. Is it in S? So it must be inside. This is an element of S1A. Is that okay? Yes. Because S1A is a subset of S already. S is a subset of S1A. So what does this imply? It means S1A is a left ideal, okay? So that S1A is a left ideal. A left ideal of S containing what? A. Thus, I have, so left ideal containing A, it means A is a subset of S1A. Okay? Why is this true? Because A is the principal left ideal generated by small a. So it will be a subset of any left ideal containing that small a, because it's the intersection of all of them. Do you get it? Now, how about the other inclusion? The other inclusion is clear. It is clear. It is clear that what? You know, S1A is a subset of A, since A is an ideal. Since capital A is an ideal containing A. This is clear. So this second equation that I'm looking for is clear. Why? Why is it clear? Because if you take any element here, if I take any x from here and multiply with this, I get this result is either, if x is 1, this is equal to A, which is an element of capital A. And if x is not 1, this x must be in S. In S. And this capital A satisfy SA is contained in A. So you have an element of S and an element of the capital A. This must also be inside A. So this product is always in capital A whenever this is coming from S1. So that's why I said this is clear. I hope it's okay. So equality holds. Capital A is S1A. So this is the left ideal generated by A. The proof is similar for the other ideals, right and two-sided ideal. The proof is similar. I hope it's okay. So this is how you arrive at the principal left, right, and two-sided ideal generated by an element in the semigroup. Okay? So next we define the notion of morphism, semigroup morphism. So definition. So that is why there, when I asked you, it was okay. Say 5n is the principal ideal generated by 5. And so, and that is all multiples of 5. And so on. So you can always do that. I hope it's okay. Okay? Now, so let A, S, and T be two semigroups in a map theta from S to T is called a morphism or homomorphism. But homomorphism here, semigroup homomorphism. But then the more general name from the categorical point of view is morphism. Okay? So a morphism, in fact, it's the one we are going to be using. So a morphism is a mapping from one semigroup to the other, satisfying this theta AB is equal to theta A, theta B. Let me just, so this is it, okay? So this mapping is what we call a morphism or homomorphism. If S and T are monoids, then a mapping is called a morphism. So monoid morphism will differ from the semigroup morphism. A mapping theta from S to T is called a morphism if, so this time around monoid morphism. Two conditions, theta AB is equal to theta A, theta B. The third condition is that theta 1 should be equal to 1. Now the identity must map to the identity. So you see, in group theory, if you have this condition, the other one is automatic. Nobody is pronouncing this condition in group theory. Why? Because the existence of inverses along with this first condition will imply the second condition. So that's why in group theory, once you define this preservation of composition, it suffices in defining morphisms. But in semigroup theory, if you define a morphism just using this condition, it stops at the level of being a morphism of semigroups. If there are identity and you are within the category of morphism, monoids are your category, you know. Morphisms in the category of monoids will be monoid homomorphisms, not semigroup homomorphism. And there is difference between monoid homomorphism and semigroup homomorphism. Why? Because you also require the what? The inverse, the identity to be preserved. I hope it's okay. But you can have semigroup. In fact, let me give you an example of this. So let me give you an example so that you can. If you take, for example, the semigroup of natural numbers, let S be the semigroup of natural numbers. Let me call it with multiplication. And T be the semigroup of integers. Let me say with multiplication also. These are semigroup, not groups. If you define theta from S to T by theta n is equal to 0. Is this a morphism? No. It's a morphism. So as semigroups, this is a morphism. But as monoid, they are not morphism. Because this is a monoid identity is there. And that is also a monoid identity is there. But you can see the identity is not mapped to identity. In fact, that is not true. Because 1 will still map to 0. So in semigroup, you can have homomorphisms, but not preserving identity, which was an automatic implication of this condition in group theory. I hope it's okay. So you have to understand that semigroup theory actually differ. There you will be seeing some unusual behavior with certain concept you are already familiar with in group theory. So don't make the mistake of assuming automatically that if I am dealing with a semigroup homomorphism, identity must be preserved. No, it's not automatic. I hope it's okay. And or inverses must be preserved. In fact, you don't even have inverses in semigroup. But then there will be semigroups with inverses. We are coming to that. Okay? So even if semigroup is with inverses, the preservation of inverse may not be automatic for homomorphisms. Okay? Or morphisms. So that is why we are calling them morphisms. So you have to always distinguish between semigroup morphisms and monoid morphisms. Okay? All right. So let me define the other notions now for so a semigroup morphism theta from S to T, I'm talking about semigroup morphism, is called, well, number one, a monomorphism. If, remember our definition of monomorphism in category theory, if uh, for all what? Semigroups, for every other semigroup U, and every morphisms for all semigroups U and all morphisms alpha beta from U into S. It is true, so this is a categorical definition of monomorphism. It is true that, so we can do the composition bar. Theta after alpha is equal to theta after beta. So composite will implies alpha is equal to beta. So if you can cancel theta from the left, then theta is 1 to 1. It's a monomorphism. Okay? Show that theta is a monomorphism. Morphism if and only if theta is 1 to 1. As a mapping. Okay? But this is a categorical form of the definition. You remember we did that in our category theory course. Okay? So we call it, theta is called an isomorphism. Isomorphism. If there is another morphism called a morphism phi from T to S such that theta, theta after phi, this will be the identity on, okay, on T, and phi after theta will be identity on S, equal to And then you can equally show that here that a morphism is an isomorphism if and only if it is a bijection, both one, one, and onto. But this is a categorical way of defining it. Okay? Now, if there is an isomorphism, uh, isomorphism theta from S to T, we say that S and T are isomorphic and write S is isomorphic to, sorry, this is, and write S is isomorphic to T. So this is what we write. This notion of isomorphism, if S is isomorphic to T, as far as algebraic semigroup property are concerned, we consider S and T as one and the same. So we don't see them as different semigroups. If you are talking about their semigroup property, algebraically, they are considered to be one and the same. I hope it's okay. So this is isomorphism. In the next class, we are going to pick from this point the concept of homomorphism, isomorphism, and then we build on from that notion. I think one last thing I have to mention is the concept of direct product of semigroups, and then we'll also talk about introducing full transformation semigroup. And then we are going to prove the analog of Cayley theorem, that every semigroup can be embedded in such a full transformation semigroup. I think this is what we are going to do in the next class. Thank you very much.